So, we're going to talk about tree data structures.
Okay.
At this point, we've talked about list-based data structures. So, if we think about data structures from the ground up, we think about them as being built using linked or static structures, that is, linked lists or arrays, are the basis for it, right?
Hey, wait a sec. You never actually taught us, like we built our own linked list, but you never actually showed us what the actual built-in linked list ones are.
I will, eventually.
Okay.
Yeah.
Sorry for interrupting.
They're easy enough, but yeah, we'll use them eventually, probably, maybe. All right, so data structures in general are built either using linked or static structures like linked lists or arrays. That is true as long as the structures look like an array. That is, a node connected to another node, connected to another node, connected to another node. When we branch off into trees, maybe the simplest definition of a tree, because we're going to talk about generic trees first. Next time we'll talk about binary trees. But we're going to talk about generic trees first. In a generic tree, every node has 0 or more next nodes. We're not limited to a single next node, like a linked list or a stack. That make sense?
No.
Okay, so a tree, we can have the beginning of the tree, and that guy can go in 5 different directions.
Mm-hmm.
And each of those directions can go in 2 different directions. Each of those directions can go in 3 different directions.
Okay.
So on and so forth.
Like the way everything extends objects?
Well, I mean, that would be a tree. A hierarchy would be a tree. But trees would look something like this.
You know what you're saying, I was just asking if that's an example.
Yeah, it would be an example. You'd have the root of the tree, and then you have some nodes that come off the root of the tree. And then you might have a node that comes off of one of those guys, and a node that comes off another one of those guys. And then maybe this guy has 2 nodes. Like that. Make sense?
Mm-hmm.
Okay. So this would be an example of what's called an n-ary tree.
N-ary.
An n-ary tree. That is a tree that sets no rules for the number of children each node has. So this node happens to have 3 child nodes. This node has 1 child node. This node has 0 child nodes. This node has 1 child node. This node has 2 child nodes.
Mm-hmm.
So each of these nodes in an n-ary tree has to have an arbitrary number of children, right? How do we store an arbitrary number of things? I've already asked this question once today. What's the difference between a linked list and an array? Arrays hold something where we know how many elements we need to hold.
Yeah.
Linked lists hold a number of things that we don't know how many elements we need to hold. Okay, so each node would have a collection, a linked list of child nodes. And that linked list might be empty, or it might have actual nodes in it. Right? So a node maybe has a payload. So what we're going to start thinking about here is that data structures may become less complex, more general, if you will. We think of a linked list, for example, as being a bunch of nodes hooked together where each node holds some data, right? Does it have to hold data, or can it link to another node? Maybe it's just the structure that just is. The data that it holds may not be the complex part. The way it's connected might be the complex part. Make sense? For instance, let's say we were storing a password. Just kind of thinking outside the box here. If I was storing a password, do I actually need to store the actual elements of the password, or could I have the password stored in the structure of a data structure? I guess what I'm saying by that is I can have a password, I can write it down on a piece of paper. Or I can have a set of clues that allows you to come upon that password. Derive the password, if you will. Right? Both of those ways are valid ways of storing a password, correct? I can either actually store it or have enough information that you can figure it out. Are both of those ways equally valid? Yeah, they both let you store the password, right? So could just as much information be stored in the structure of something, how something is put together, how it's linked from one thing to another thing to another thing? Could just as much information potentially be stored in that as opposed to actually physically stored inside the payload of an individual object? That's the whole point of like the game Pictionary, right? You can draw a picture of something and that's enough of a clue that you get the answer. Make sense? I mean, it's a little bit of a stretch what we're talking about here, but I mean, the point is that the data doesn't always have to be obvious. Sometimes the structure is the data. All right? But for right now, we're going to say our node will hold a payload because when we teach trees, that makes the most sense. All right. Now, our node is also going to have a linked list of child nodes. Okay? Linked list of child nodes. Now we have an issue. Let's close all these. Well, you should use driver here for a few minutes. We have a problem. The problem is in our current version of our linked list that we wrote, linked list holds connections of nodes. And each of our nodes knows how to hold a payload, right? But also each of our nodes only knows about a single next node. Well, that starts becoming problematic, correct? No, we can't have that. So, rather than write our own linked list, because we'd have to rewrite this guy, right? We have to say, oh, okay, well, a node is now has an int payload, but instead of having a single next node, now it has a linked list of nodes. Now we're implementing a linked list in terms of itself. Kind of make sense? Well, every single time we need a linked list, we could create a brand new linked list class of our own, change the way the payload, some of them are built for holding ints, some of them are built for holding chars, some of them are built for holding alligators, whatever we decide we're going to hold in our linked list. We have to re-implement the entire linked list for each of those. Or, as Lauren was asking, we could use the built-in linked list class, which uses something called generics. I'm going to show us how to do this out here in driver. So I'm going to, let's do it this way. Get rid of node, get rid of linked list for right now. I'm just going to quickly create a linked list of strings. Okay? So we're going to say linked list. Well, I'm going to start off writing a generic linked list, and then I'll show you how generics work. So linked list, let's cut LL is equal to new linked list. Now, right now, this guy is pulling from the linked list that we wrote here. Okay? I'm going to go ahead and I'm going to delete that guy. Don't need him anymore. Yeah, get rid of him. I'm going to go ahead, I'm going to delete node too. Don't need him anymore. I'm going to delete stack. Don't need him anymore. We'll delete huge integer. Done with that guy. Delete elastic array. Okay, good enough. Now that I've gotten rid of our linked list class that lived inside of our default package, now this guy doesn't know about linked list anymore. So if I highlight over this, it says, oh, you want linked list? You want to import java.util.linked list. So I'll go ahead and do that. I'll get rid of this java.util.random. We're not using it right now. So now I'm building a generic linked list. Now, I'm going to go ahead, I'm going to add 3 strings to our linked list. So I'm going to say ll.add. Now notice the add method here inside of linked list takes an object. So they've essentially created their nodes to hold generic objects, because that's the most generic an object can be, right? We could create our own generic linked list that holds anything, because anything can become an object at its most top level, correct? Anything could become an object at its most top level. Therefore, the best way, or the most general way, of developing your own linked list would be write it to take in objects. And then you can store whatever you wanted in there, and then when they came out, you could typecast them back to whatever they actually were. So if you had an elephant object, and you put it into a linked list that expects an object, it would store it generically. It's still an elephant, but when it gave it back to me, it would give it back to me as a generic object. I would then have to say, oh, by the way, you're actually an elephant. Typecast it back to elephant. Not a big deal, but usually, and I'll show you that by example here. So we're going to add cat, dog,
Okay.
elephant. All right. The add method here takes in string, or takes in objects. I passed it a string. A string is an object. It is one of those guys, okay? But it's more. It's more than just an object. It's a string. Now I'm going to say ll.get. And this guy allows me to say what index I want to get from. So if I say ll.get, I'll print it out actually. Say system.out.println ll.get 0. This is going to get me that cat.
But why is it going to get you a memory address?
Why isn't it? I'll let you answer that in a second. Okay, so this is going to get me, now notice again, when I say ll.get, it's taking in an index. I'm going to pass it 0. Give me the first element in our list. And it's returning an object. Okay? Not a string, an object. Because I'm using the generic linked list. So I say, give me the thing at bucket 0. The thing at bucket 0 should be cat. So it prints out cat. She asked, well, why doesn't it give you a memory address if it's returning an object? Well, what's the answer to that? That would be a good quiz question.
You don't get quizzes though.
Well, I could.
Maybe just because object in, object out.
They're just making crap up.
Or,
You should know the answer to this.
You got okay.
It's because memory addresses are where it's where the pointer's pointing to, and then
If we create a generic object, so here we'll go back to our random object. So I'll comment this out. We'll say random r is equal to new random, and I say system.out.println r. What's going to print out? Memory address, right? Well, it's going to want me to import java.util.random first because I just deleted that. When I print out R is an instance of the random class. The random class is an object. So when I print out R, it's going to print out a memory address.
Isn't that because of the
String S is equal to new string blah. We'll even use a new keyword so we know what memory address is involved. If I print out S, what's going to print out? It's going to print out blah.
string is object?
I like frustrating her.
yeah, I noticed.
Why? See, Habib's all happy that he got it right, but can you tell me why you're right?
Yeah, just like we are not defining anything there, so just it will take the random memory address. And yeah, once we're taking a string, just it's displaying the string.
Okay, but why? The trick has to do with the fact that the way I'm displaying it is by saying system.out.println. Whether I put an S there or an R there. By putting an R there, it showed me a memory address. By putting an S there, it showed me blah, not the memory address. Why? What does system.out.println do
Yeah, just
when
it
you
will print-
pass it an object?
Yeah, like it will print the value of the object. So
Mm.
we are
Very, very specifically, what does system.out.println do when I pass it an object? It's a extremely specific thing that it does, that we've done in this class. Or not, we haven't used it today, but we've done it in this course so far, and we did it a lot in 535. Very, very, very specifically, system.out.println, when I pass it S or I pass it R, it actually calls what?
Yeah.
Library.
You're just saying words.
No, Java library.
polymorphism.
Polymorphism. No, now you're just saying words. There's something hidden right here.
ToString?
ToString. R.ToString is what's actually getting printed out. R.ToString looks like that. S.ToString looks like that. Why? Who created the first ToString? Object, right? Top of the hierarchy, we have the ToString that object provided us. R, our instance of random, he was lazy and said, you know what? I'm just going to take advantage of the old natural ToString that object gave me. And that's why my ToString shows crazy memory address just like object's ToString does. Why? Because I didn't rewrite it. I just used the one that was handed to me from my probably great-great-grandparent. Thinking random was probably 2 or 3 levels down. But S says, look, I'm a modern object. I don't need to live back in the Stone Age like generic objects. I wrote my own version of ToString, which superseded the more local one. That version of ToString prints out what I really look like, not my memory address. Does that make sense? So, ll.add. Okay, so everything I've said so far makes sense. So I'm about to try to trick you. Prepare to be tricked. Nothing up my sleeves.
Don't wear sleeves.
Well, that's how you know nothing's up then, right? Hold on, what was I about to do?
Trick us.
Oh, that's right. Trick you. Here, I'll comment out these things. Yeah, how bad is it going to be if I trick you and I didn't even remember what I was going to do? Very sad, people. All right, so we have our linked list, a generic linked list. We're going to add cat, dog, and elephant to it. And here, if it makes you feel better, new string.
Is that part of the trick?
Well, it's not, actually. I just want to make sure that we're literally comparing apples to apples here. It actually literally makes no difference in what the answer to this trick is.
Well,
Just
doesn't it make a different memory address?
it does, but from what we're doing here, it won't make any difference in the output. But I'm just doing it so it completely matches what we did down here. So we physically are calling the new keyword to create our string as opposed to letting the syntactic sugar thing do it for us. So I added 3 strings, 3 fresh, brand new strings to our linked list. Then I get the string at bucket 0. Now again, just to show you, ll.get returns an object. And objects have what? They have a toString method. And what does objects toString method do?
It prints whatever it decided to string.
Prints out, well, what does objects
Yeah.
toString method do? Prints out memory address.
Oh, okay.
The generic toString method prints out a memory address. I'm going to say, get me the object that lives at bucket 0. What's going to print out here?
Cat.
Think cat, because you've already seen the answer. We already showed this once. Why? Why did it print out cat and not a memory address?
Because you said it's the string, so it has a special ToString thing.
Okay, but ll.get returns an object, not a string.
Yeah, like we're using typecasting here, so we're
I'm not typecasting anything. If I typecasted, I would do this. Now I typecasted. I said, look, treat this generic object like a string. Now it's typecast. But without doing that, no typecasting. So it goes back to our old question that we keep coming up with in this class. We can guess what the answer is going to be, but we don't know why the answer is what it is. So let me give you an example. Everybody here know who LeBron James is?
Yes.
Lauren? You know who LeBron.
Once heard.
You what?
You were once said about LeBron James.
LeBron James, basketball guy,
Basketball.
right? Really good basketball player. Okay? So, we're going to take LeBron James. But we're going to put him in a mask. Put him in a costume. Okay? So, if I gave a person wearing a costume, a basketball, and that person was actually LeBron James, could he still dunk like LeBron James? Sure, because he is LeBron James, even though he didn't appear to be LeBron James. Looked like him. Didn't look like him. But he was him. This guy that came out of our linked list did not look like a string because he came out in a costume. He came out looking very plain and generic, like a generic object. But that doesn't change the fact that he was a string. Okay? Now, here's the catch. An object has a ToString method, correct? Strings also have a ToString method. How many ToString methods do strings have?
One. Yeah, we can use like subclass 2.
They have 2 of them. They have the one they inherited from their parent. And then they have the one that they wrote locally that overrides that one. It hides it. It allows us not to be able to access it external to string. But if we are inside of the string class, we can access our parents' ToString. And we've seen this. If I write my own class here, let's see here. I'm just going to create a quick node class. We're going to be using that anyways. Oh, here. I'm done. We'll go ahead and add 3 new nodes to our list. And then we're going to tell our linked list to print out the object, which happens to be a node. But we know, because we are intermediate to advanced programmers, that there's a hidden thing here that says extends object, right? This class node actually is an object, but he's a little bit more. So we're going to add 3 brand new nodes to our linked list. And notice that nodes are extremely complex objects that literally do nothing. Okay? Just complete waste of space. We're going to add them to our linked list. Then we're going to get the one from bucket 0. Notice, again, this guy's going to come out as an object. Even though he's a node, it's going to come out as an object. I'm going to say, get me the one at bucket 0. What's this going to print? Memory address. I wrote my own ToString, overriding the one I got from my parent. Now what's that guy going to print? He's going to print boo. Because I changed the one I got from my parent. That makes sense? Inside of node here, I originally got my parent's ToString method. But I chose to write my own more local one that says boo. Go ahead.
So if you write underneath your public string ToString, if you write super object, then
Super object.
doesn't super, wouldn't that bring it back up to object and then unoverride it?
You can't unoverride it. Once you've overridden it, you've overridden it. But you can use your parents inside of this. I could say print out boo, then concatenate onto that super dot ToString. And this will print out boo followed by memory address.
Wait. What? Go back.
I wish I had more lines of code here. I could do my scrolly thing.
Super parent. Oh, plus the parent of that method. Okay.
So I asked a few minutes ago, how many toStrings method does string have? String has 2. It has the one that they wrote. Just like me asking, how many toString methods does Node have? Node has 2. It has the one that we wrote right here. And it also has the one that our parent gave us. That makes sense? Even though we overrode it with our more local one, we can still access our parents inside of here. Because only inside of this particular instance of Node do we have a direct link to our parent through the super keyword. But out here in driver, when I say ll.getZero, this guy is still calling the toString method. Whether we like it or not, what I have highlighted there is on the end of that. It's appended there, regardless. That's what the println method does. It appends that. Okay? So, the question is how does this resolve? It resolves just like variables do, to the most local definition of the toString method. So the first thing it'll do is it'll ask this guy, our masked node, our generic object that is actually a node. It'll say, hey, mystery man, call your toString method. Node will then look locally. Ah, I have one right here. I'll take off the super one thing here for a second. And his local one says to do what? Print out boo. Don't print out the memory address. Don't look any further. You don't have to look up my parent. I have one right here. So it'll print out boo. Similarly, if we don't name that toString, name it something else, something that does not override the one we got from our parent, we print this out, it'll print out memory address. Make sense? Because what it did is he asked the mystery man, do you have a toString method? He looked internally here and said, no, I don't. Let me check with the boss. So he passed that request up the hierarchy and said, do you have a toString method? This dude's asking. Make sense? And that's how it eventually goes up. But inside of our node, we do have access to our parents' toString. Because it's reasonable to think that, hey, I might want to take advantage of a method that my parent used to have, but I might want to augment it with my own stuff. Why reinvent the wheel? If my parent already does some stuff that I think is good, I just want to do a bit more, you might choose to do something like this. This is the method that allows us to augment it. Make sense? Okay. So, that is why out here, nodes printed out memory addresses initially until we wrote our own toString, but strings printed out strings, even though they both came out of the linked list as objects. Just because you come out in costume doesn't mean that you are not what you used to be. That make sense? You're just still wearing your costume. You still look like a generic object, but you still are a string, and you still are a node. Just the runtime of your program doesn't necessarily know that until you typecast it back to what it is. In this case, though, we don't need to typecast it. Why? We're asking it to call a method that all objects have. Whether you're a string, a cat, a dog, a node, or an object, Java knows that all objects derive from the top level object, and the top level object provides a toString method. Therefore, every object has a toString method, whether they try to create one or not. Make sense? Okay. Now, this is our generic linked list, the guy we have right here. But wouldn't it be nice to be able to create a linked list of strings, or a linked list of nodes, or a linked list of whatever. Because usually when we're creating linked lists of things, we don't want to have the problem, or the inconvenience, if you will, of asking for something at a certain bucket in the linked list, then having to turn it back into a node, then calling upon kind of a non-global method. So something other than ToString. So for instance, let's say that we had, well, let's just change this guy to Greg. So we got a method named Greg inside of node. We know that that guy will be a node, correct? For a fact. We know it's a node because we're the one who put him in there. Yet when I say dot Greg, it's not a happy camper. Why not? Hover over it. It says the method Greg is undefined for the type object. But ToString wasn't. That's why it didn't give us the problem with ToString. Make sense? But Greg, hey, look, whether this guy is in costume or not, I'm the compiler here. And I'm telling you, this guy looks like an object. And objects don't have methods named Greg. Therefore, I'm going to scream at you. Okay? I can turn this guy into a node. So I typecast him as a node by putting open parenthesis node, close parenthesis in front of ll.getZero. Then I wrap that entire thing inside of a parenthesis. So what I have highlighted right there ultimately is an instance of a node. We've removed the costume. That's what typecasting did. Now we can call his Greg method. Make sense? And what does this Greg method do? Returns boo, followed by whatever the ToString method says to do. Okay? We would all call this an inconvenience, though, correct? I mean, this was a lot. I mean, this is an inconvenience. If we have to do that tons of times as they're writing our program, constantly typecast stuff, that's a problem. It's not impossible. We can certainly do it, but it's an inconvenience. It's something that we wouldn't want to do. Java has fixed this through something called generics. So even though the linked list class in Java is written generically, that is, you can store anything in there that is an object, when you create that linked list, there's a special syntax called generics where we can tell the linked list constructor what kind of object specifically this particular linked list is built for holding. So when I build this guy, I could say linked list of type node LL is equal to a new linked list of type node. Now notice when I come in here and I say LL.get, notice this guy returns a node now, not an object. Generics, which is this angle bracket node angle bracket thing I wrote right here and wrote right here, that special syntax has let this particular instance of linked list know that, hey, you actually return a node, not a generic object. Since you're a node, you have access to a Greg method. Make sense? That's the convenience it gives us. A little extra syntax right up here, and now our generic linked list can hold much more specific values. It's not doing anything that the generic linked list didn't do. It's just saving us from having to do typecasting. The stuff comes out and goes in as what it was. Nobody has to put a costume on. Make sense? Okay, So questions about that? And there's your linked list. Learn. Now, traversing linked lists. For int I is equal to 0, I is less than ll dot size, I plus plus, system dot out dot println, ll dot get, I dot Greg. So that'll spin through every bucket of this linked list, calling the Greg method on each of those nodes. Similarly, linked lists also support iterators. We've done for each loops in here, right? Did we do it in the 535 class at least?
For each?
Well, I'm going to show it to you again anyways.
Fairly short to us, but then not really.
Okay. An equivalent to this would be this.
Colon or something.
For node n in LL, these two loops do the exact same thing. This one goes through bucket 0 to bucket size minus 1, gets the node at each bucket, calls Greg on it. This guy says, for each node named n in a linked list named LL, print out n.greg. So these will both do the exact same thing. This syntax for each loops works with something called an iterator in Java. I'm not going to go into that too far other than you have to implement the interface called iterator in order for each loops to work. So what I want you to take from this is that linked lists in Java do implement the iterator, just as arrays do. So if I had an array of strings, I can say for string s colon whatever the name of my array is, that would go through every element of the array as well. The downside to a for each loop, you don't know which particular bucket you're at. You can't say, am I at bucket 5? Am I at bucket 6? You don't know the numbers. You do know the number here. But the nice thing about for each loops, you don't have to do ll.getI, whatever. You have it right here in end. So, again, for each loop is not an upgrade to a for loop. It solves certain problems where for loops solve other problems. It's never wrong to use a for loop. It's sometimes wrong to use a for each loop. For loops will always be able to solve every problem a for loop can solve, but possibly with a little extra work. Okay, so that's how you would spin through. So ll.size is to a linked list, as s.length is to a string with the parentheses, as ar.length with no parentheses is to an array. Tells us how many elements are in it. All right, questions about the linked list that's built into Java. Good news here is now you're allowed to use it. I've released it in the class. So now you can use the built-in linked list class for your future assignments. Okay, now let's do something impossible. We were talking about trees. A tree looks like something like this, right? Mm-hmm. So if the definition of a tree of an n-ary tree is, how many O's was I going to put on there? Is a root node with 0 or more child nodes and a payload. If we say that an n-ary, well, forget about the payload actually, unimportant in this example. If we say the definition of an n-ary tree is a root node followed by 0 or more child nodes. It's a pretty simple definition, right? Well, so are stacks. All these data structures are simple. There's not a whole lot to them in substance. It's all how we use it, right? That's where the magic happens. So, is this guy a tree? How many trees do you see on the screen right now?
2.
3.
3?
Oh, yeah.
I have here 2. I have 3. 3?
8.
8?
3.
Oh, you changed yours to 3?
Yeah.
Okay.
It's 3.
What do you guys think in the back there? How many trees?
There's 1 I would actually.
Yeah, see, they're not paying attention. That's why I called on them. How many trees do we see here? Definition of a tree is a root node followed by 0 or more child nodes. Is this guy a root node?
Yes.
Does he have 0 or more child nodes? He's 3. This guy a node? Does he have 0 or more child nodes? Yeah, he has 1.
But
This guy a node?
not root node.
What is a root node?
Main, like a father.
Who made that up?
You did.
Oh, okay. Fine. Father. This guy is the father of these 3. Is this guy the father of this guy? Is this guy the father of this guy? Is this guy the father of this guy? Is this guy the father of unborn children? Every node is a tree. So a tree is a node followed by a collection of 0 or more trees. It's an important distinction that tree and node are synonyms. Every node of a tree is in itself a tree.
That's right.
So, that make sense? Now, the good thing about that, this relates to what we were had in our paper, is little bells should be going off saying, recursion is a possibility here. If every single one of these nodes is the same kind of animal, every one of them will have the same methods. I almost call this fake recursion, because you're not actually having a method call itself. You're having a method call the same method of another tree. So it's kind of like calling its own method, but it's calling a method extremely similar to its own method, except it actually belongs to somebody else. It's kind of like if you live in one of those neighborhoods where all the houses look the same, and you run over to your neighbors to use the bathroom. It technically is just like your bathroom at home, but it is somebody else's bathroom. It was a perfect example. Everybody got what I was saying, right? All right. Now, what kind of stuff, if I showed you a structure like this, what kind of stuff might you store in a tree? Okay, so we have something like this. Great. But first of all, why is it called a tree?
It's like connected.
Well, why are they called linked lists? Because it's a list. Linear, right? And it's all linked together. Hence linked list. Why is this guy called a tree? What does it look like? Looks like an upside down tree. If you went outside, took a tree, uprooted it, and turned it upside down, it would look like this. Right? Okay, so this guy, that's why it's called a tree. It looks like an upside down tree. Why didn't they call it an upside down tree? Because they were lazy. I'm sure that's factual. Okay, so now that we know what a generic tree is, an n-ary tree, I'm calling n-ary trees generic trees because they don't follow any rules. Next class, when we talk about binary trees follow a very specific set of rules. Okay, they're always sorted. That's your hint for next class. Unimportant here. N-ary trees are actually more difficult to work with. binary trees are easier to work with because you know exactly what to expect. N-ary trees, every single time you run into a node or another tree, you don't necessarily know how many branches come off that particular limb. Right? What types of things might you store in a structure like this? Say this again? Okay, what kind of data?
You just said
We
passwords.
can store objects, strings.
Okay. Passwords, objects as strings. Give me an example of how you would store strings.
We can store name. We can store like database numbers.
Okay, why would I store names in a tree instead of a linked list? Let's talk about that. So let's throw into my question, what is this guy the right tool for the job?
Yeah, like if I have the bank account, so it's on my name. So like I'm the parent class. So like everything was under my account. So I want to be stored in my like child nodes, like my balance and yeah, what are transaction I'm making. So everything goes into the child nodes.
Okay, let's let me extend that a little bit to give us our example. Let's say at the top level here we have Habib. And this is morning, afternoon, and evening. He's divided up his day into 3 subcategories. It's a very rare thing. It's actually an inside joke in my family. About 8 years ago or something like that, when I lived in Illinois with my wife, we were driving down the street, and I don't remember what we were talking about, but I said something to her, you know, I like to divide my day into 3 parts. I think about it as morning, afternoon, and evening. She just starts busting up laughing because, you know, like everybody thinks about their day in morning, afternoon, evening, right? But I guess the way I said it, I acted like I invented those terms, which I did. I'd never heard them before that day. Okay, so anyways, top level, this is Habib. Morning, afternoon, evening. Here's a task he does in the morning. He doesn't do crap in the afternoon. Here's a task he does in the evening. And that task has 2 subtasks associated with it. That might be the type of data you store in a tree.
They're like the folders in a computer.
Could be the folders in a computer. Think about your C drive on your Windows machine. That's the top level of the tree. Inside of that, you have some number of folders. What's each folder? Each folder is a collection of other folders and files. Each of those folders is a collection of other folders and files.
That's one called tree that time.
Yeah. Files in tree nomenclature, that's a good word. I haven't said that word in years, it seems like. Files in tree nomenclature would be called leaves. Leaves. Folders in tree nomenclature would be called nodes. Or, interchangeably, trees. Make sense? Okay. Now I'm looking, if you haven't noticed yet, I like to gamify all my lessons. Turn it into little games. That's fun, right?
Of course.
Yeah, we gotta do game stuff. We always gotta have a smile on our face. Like you spent what? 17 hours yesterday not finishing my assignment?
Yeah.
And you're smiling? You're happy, you're jolly.
Because I learned a lot of stuff.
See? You would have learned more if you would have started earlier. Then you could have spent 60 or 70 hours on it.
No. I have other 2 classes.
I'm not worth 60 or 70 hours.
No, you were, but I have 2 more other classes.
I always think it's funny. Students think like their teachers, like when they don't put effort into an assignment or something like that, they think they have like offended their teachers. Well, I don't care. This is your life. I get paid either way. I do think it's funny to make fun of you, though. I like it. I actually especially like making fun of her because it upsets her.
It's not.
Oh, I think it is.
It is not.
All right. So, we're going to want to turn this into some sort of game, right? Now, what kind of thing could this be? Where, well, let's think about this. Oh, I have a good idea. We're going to build a dungeon crawler. This is a dungeon. Each of these are rooms in our dungeon.
One time we did that in 6th grade. There was this computer program we're selling, and like they called them cards, and then we had to like apply stuff, and so like, and then we had to create like little buttons on the card. Then if you click like left or right, and it was like an adventure, and then when you got
okay,
it was really weird.
No, I know what you're saying.
Yeah.
Did you ask what a you didn't have? Do you not have dungeons in Kazakhstan?
I don't understand. Maybe we have, but I don't.
It's like a cave. You go into a cave, and there's a bunch of rooms.
It's like an underground prison cell.
Yeah, underground prison cells. You have those all over the place in Kazakhstan.
Like the dark and gloomy face.
Yeah, you know that, right?
Oh my gosh. All right, so we're going to create a dungeon crawler. Now, historically, this might be called something like Dungeons and Dragons or something like that. Okay? Where you are a hero. Okay, so you're a guy. And you are traversing the dungeon. All right? And so maybe we start off at the entrance, the root node. So we're at the entrance of our dungeon. Inside of each room of our dungeon, we're going to have a description. And you might have other creatures.
They already have this built into the Mac terminal.
Oh yeah, they have all this thing's been built a zillion times. But we're going to make ours better, I'm sure. So, we're going to create a room. A room is going to have a description. It's also going to have a linked list of exits to other rooms. That make sense?
But can you go back?
Well, possibly. We'll have to think about it. We'll have to think about it. We'll have to see how far we get here for me to give you your correct assignment.
Sure.
So description, linked list of exits, and we will allow there to be one. Well, no, I was going to say we can have an enemy in the room. Maybe we might leave that for next class. So no enemies in the room. We can't fight anything. Right now we're, what's it called, spelunking? We are going into the dungeon and just checking things out. Okay? So every room has a description and has a linked list of exits. So as an example, you might be in a room that says, a dark and murky room. And then you might have something that says, obvious exits. North, south, east, or something like that. Now, maybe for our purposes, to make this relatively easy for us, since our tree looks like this, we'll say obvious exits are 0, 1, 2. Okay?
Or you could just create an array with the...
Well, we could. Maybe we'll add that. We want to build our skeletal structure of our cave. This might be a 2-class type thing, where we'll have our first part of the assignment due next class, and then we'll continue on from there. So obvious exits we're going to treat like an array. 0, 1, 2. So if we were in this room's going to have a description. Maybe the description is just room 0. And obvious exits are 0, 1, 2. If we're in this room, it's going to have its generic description. Obvious exits are 0. If we're in this room, no obvious exits. If we're in this room, obvious exits are 0. It'd be 0. There's only one of them, right? One child. So this would be 0. This guy has an exit 0, and an exit 1. This guy has no exits. This guy has no exits. That makes sense?
Mm-hmm.
Okay. Now, now we're going to gamify it. Here we're going to gamify our. We're going to build in a random number generator. Oh, this could be awesome. I just invented a new fun game. We're going to write this. We're going to sell it in the App Store. We're going to make easily like $3, $4.
Anyone ever needs the definition of anticlimactic? I will pull up this recording.
Okay, so a room also has a small chance of having treasure. If you enter a room that has treasure, you get a point. The point of our game is to randomly generate a dungeon, walk through that dungeon by our own choices. So this answers her question of, can you go backwards? We're going to say no. So you have to make the right choices to get the most number of points. So let's say this was our linked list, or our tree rather. If we chose to go this route, we only have 2 nodes to work with.
So are you saying that we're gonna randomly generate the whole tree with all its branches and leaves and stuff, and then when we get to the end, it brings you back to the beginning and displays your points?
We can try again, so you can start memorizing the structure of the tree.
No, but I'm saying, are we gonna have? No, you're making it too simple. Wouldn't you want to make it so that it randomly generates a whole different tree the next time?
No, because then there's no skill involved.
Well,
so let me give you an example here. So I'm going to say we're going to put treasure here.
What's the difference between you and me is that you're always going for the skill games.
Well, otherwise it's just a stupid game.
Yeah, but they're time.
We're going to put treasure there. We're going to put treasure there. We're going to put treasure here. And we'll put treasure here. Okay? So, follow this. We're going to start here. So we always enter our game at the top root node. From here, you choose a direction. So we choose either to go 0, 1, or 2. I actually think this could be a cool game.
But will there eventually be a point where we can eventually completely start over and create a new
Oh, yeah. So follow me here. So we'll start off here. So now it's choose your own adventure. We have no information other than here are the exits. Pick a door. So we'll pick door 0, let's say. Process of elimination. So we're at door 0. Is there treasure in here? No, we didn't get a point. But there is one more door. Go in here, we got 1 point. But we're out of doors. So right now, our high score is 1. Okay? So since we're out of exits, it's going to bounce us back to the beginning. Okay? Now we're back at the beginning. We can try again. We know if we go here, we're going to get 1 point. So we're not going to go there again, right? Because we remember. We learned. We have 2 more doors to try. So we're going to go to this door. We got 1 point. So now our current total is 1. Now we're out of exits. Done. Did we beat our top score? No. Go back up. Now we're back at 0. Go to our last door. We got 1. We only got 1 choice here. Go there. We got 1. Let's say we go here. So now we have 2 points, beat our top score, but can we do better? Bounce back up. Go here. 2, 3. Top score was 3. And that's completing the map, is getting the top score. The most number of points that you can traverse the tree with. That make sense? This is kind of a cool game. For like an iPhone game, wouldn't this be kind of fun?
There's so many of those that I've played.
Yeah, so many of them that make. Easily enough money to buy lunch. All right.
Why would you pay for apps when you can just illegally download them?
We have to start all the time from
Spoken like somebody who was before class was talking about how they want the education system to be fixed. You know, the people that are that figure out how to illegally download those things are probably the smart kids from class that aren't being properly challenged by their teachers. So they're going off and putting their smart brains to frivolous activities like stealing music and stuff. Do you really want to take that away from them?
Would I really want to pay for 1,000 songs?
You like me and don't listen to music. You have options.
Listen
My
to
iTunes
radio
library
free.
is 1,184 songs.
Oh my God.
Pay for those.
My iTunes library has 0 songs.
If you have some time, I'll help you out.
No, I don't want them. My wife has music. I can get them. I just got to put on whatchamacallit.
Apple ID?
Yeah, put her Apple ID in, and then it just. Well, actually, I use her Apple ID. I just have it set up to not sync the music. It'll sync it from the cloud. iTunes Match, I think it's called. Okay, so we get what we're creating here. So we're going to need to have a way of creating our tree. All right. Now, we said that a tree, in our case, is a collection of rooms. So for the homework, we're going to have a cave. Yeah, we'll call it a cave. A cave has a room followed by 0 to 4 the easy version of this. Let's say 0 to 2 subrooms. Okay? Maybe we won't implement levels or anything in our assignment, but maybe more difficult after you clear the first board, then it goes to 0 to 3 rooms, 0 to 4 rooms, 0 to 5 rooms, so on and so forth. That make sense? Okay. The one little catch here is that we might generate a cave that randomly rolls a 0 here, so you only have 1 room. In which case, you'd instantly beat the cave. But we might put a little check in there that says that can't happen. From our perspective, it doesn't matter. It's going to be a pretty low chance that happens-ish. Not that important for this thing. So our cave is so this is a synonym for tree. Okay, so we have something called a cave, which is a tree, just like a tower was a stack. Inside our cave, we have rooms. A room is like a node.
Is there special tree syntax for like generic trees?
Oh, what do you mean tree syntax?
Well, I mean, there's linked list syntax.
Oh, you mean are trees built into Java?
Yeah.
Yes, but we can't use them. You gotta write them yourself. So a room is a node. Each room will have a 50% chance of treasure. Okay, 50% chance of treasure. This is the payload, whether or not it has treasure. A room also has 0 to 2 child rooms.
May have.
So it's going to be random. So every room will have 0, 1, or 2 child rooms. Make sense? Okay.
For finding like a 50% chance, do you just have to do a random integer from like 0 to 1, and then if it's 0, then it has treasure, if it's 1, then it doesn't?
You can do that.
Like, is there simpler than that?
That's fine. Or you can say number between 1 and 50. If it's less than or equal to 50, it's one of them. You know. So any of those is fine. Yeah, 0 or 1 is fine. I would say that's perfectly acceptable. All right. So let's go ahead and start implementing this. That way I can give you something given for your assignment. Okay. All right, so I'm going to come in here and we're going to, I'm actually just going to delete all, well, here, let me do this. We're going to create a new project.
What are we calling this game?
Oh, that's a good question. Let's just call it,
Basement.
huh? Mike's Basement? That's creepy. Let's just call it Crawler for right now. I actually really like this idea. I think I'll write this for iPhone. I think it'd be a fun game.
Yep.
All right, so we're going to create a new class in here. We'll create our driver. Okay, everything works. Now we're going to create another class in here called cave. What's a cave? A cave has one room at the top level. So we're going to have a private room called entrance. All right, but now it's screaming because we haven't written room yet. So let's pause that for a second. Let's go add new class, room. What's a room? A room may or may not have treasure. Private Boolean has treasure. And it also has a linked list of other rooms, between 0 and 2 other rooms, right? Well, we don't know if it's going to be 0, 1, or 2. Probably going to be a linked list.
What happens if you make a class private?
If you make a class private, then you could never use it.
Oh. Okay. Then why do we have to specify public for class?
You actually don't. You could leave public off.
Oh.
The only class that has to be public is the one that has main in it.
Okay.
This class absolutely has to be public because it's going to be accessed outside of the package by the Java virtual machine.
Yeah.
These other ones could potentially not have public in them. It's more just habit. But yeah, it's a good question. Okay, so public class cave. We have a private room entrance. We also have a private linked list of rooms called the exits. Dun, dun, dun. Okay, and linked list, we need to import java.util. Man, I'm really stoked about your homework. Aren't you guys excited about this?
I don't understand why is it your habit to always put like the before your variable names? I always found that amusing. Like, instead of just exit to put the cards.
That's a good point. I don't know where I picked it up. I just think this is expressive. You know, this is the linked list of the exits. I mean, I get what you're saying. It's not like a right or wrong thing, but
I just find it amusing.
yeah. I think I've been doing it for a long time. I always use it in my classes as a good example of how important some of those things are. Some of those things are, which,
Those things
which,
are.
those things is. Good,
No,
got it.
are. You just ignore the stuff after a preposition or anything in the rest of the sentence, and so is the first thing.
Right. No, it's in the rest of my life, I'm very disorganized and I'm sloppy. I just leave things laying around the house and stuff like that. But with coding, I'm very particular about variable names, indentation.
Your grammar is triple too. You're like, instead of like a versus an, like, you mix those up too.
Yeah, I don't even care. Yeah, when I wrote my dissertation.
And you end sentences with prepositions.
Oh yeah, all the time. But I do know I'm doing that, and I just think it's funny.
No, it's not.
Well, I think it is.
It's like nails on a chalkboard.
Well, yeah, but what am I don't have, there's no more degrees I can get. I have a terminal degree. I don't need to be smart anymore. But man, I would have never gotten my book I wrote for my dissertation finished if I didn't have my wife to grammar check that thing. Man, me was like a monkey doing a math problem. That grammar's terrible. Okay, so we're going to have a private linked list of exits. Now we're going to create a constructor for this cave. Public cave. This guy will take in no parameter. Oh, hold on. We're building our linked list in the wrong place. This guy has an entrance. We don't need linked list here. Caves don't have a linked list of entrances, or exits rather. Rooms have a linked list of exits. Okay? So a room has a linked list of exits and whether or not it has treasure. Public room, here's our room constructor. Inside here, we're going to generate a random number. We need two different random numbers. One of them is whether or not we have treasure. The other one is how many rooms are we going to have. Make sense? So, we're going to say random r is equal to new random. Import java.util.random.
Why doesn't it automatically do that? Why do you have to import these things?
Well, I mean, whenever we import a thing like this, when we compile our code, the executable is larger because it has to bring in other libraries. I mean, you could just say import everything, but then every one of your executables would be giant. So it would have the entire language in it. So only the stuff that's inside of java.lang is automatically available to us. All right, so random r equals new random. Now we're going to determine if we should have treasure or not. If r dot next, ooh, I like that one, has, well, we'll say this dot, has treasure is equal to r dot next boolean. I don't think I've ever used that one before. So I'm using my random object to generate a random boolean value, either true or false. We'll just assume it's a 50% chance. It's good enough. It's giving me either, it's a coin flip, boolean true or false. So I'll get my next boolean, just store that in has treasure. Then I'm going to need my number of rooms. Well, I'm going to say the exits is a new linked list of rooms. Now, linked lists are arbitrary in size. I don't have to put any rooms in there if I don't want, correct? So now I need to figure out how many rooms. For int I is equal to, that might be a little cryptic to say it that way. Int numRooms is equal to r dot next int, what did I say, 0 to 2? R dot next int 3. That'll give us a value between 0 and 3 minus 1. So 0, 1, or 2. That'll give us that value. For I equals 0, I is less than numRooms, I plus plus. Actually, let me think about this for a second. 0, 1, or 2 rooms. It's 2, 0, and 1. Yeah, okay, we're fine. So we'll say the exits dot add new room. Now what's cool here is we just did our fake recursion. I'm inside the constructor of room, right? Right here I'm calling our constructor for room, but for a new room. And that constructor is going to determine whether that room has treasure and how many exits that room has, so on and so forth. Does that make sense?
So is it going to use up like a lot of memory on the stack or something?
Depends how lucky we are. Not on the stack, because we're not actually calling it recursively. This is a brand new room. So we're not pausing this guy. We are inside of the room constructor for this particular instance of room. This is calling the room constructor for a brand new instance of room. So we're creating another room.
But
Yeah.
wait like 10 seconds. Hold on. Let me think.
Mhm.
So we're making a room, and then isn't this just making a room and then branching off and only branching in one direction? Do you know what I'm saying?
Mm-mm.
Like how we know there is exit for the.
Well, if I'm okay, let's pretend that I'm this current room. So we're inside the constructor. I'm this constructor, this particular call, and I've determined that I'm going to have 2 exits, not 0. I'm going to have 2. So I'm going to create 2 new rooms, 2 new things like me, but not me. So I'm going to say new room. So I just created a clone of myself,
Just kidding, I get it.
but a brand new one. Okay, and I added him to my linked list, my little duct tape satchel.
Go away.
All right, so I added my new room. That's another inside joke with her.
My dog ate my duct tape satchel.
Yeah, we've heard teachers have heard all the no homework done excuses.
No, my satchel.
So I'm going to create a brand new room. We're going to add it to our linked list. Then I'm going to create another room and add it to my linked list. So I'm going to create 2. But understand that each time one of those rooms is created, this constructor gets called. So I'm going to create this new object of type room. And inside of that guy's constructor, he is going to determine whether or not he has treasure. He's also going to determine how many exits he should have. He's also going to determine, well, he's also then going to build his exits.
Keep creating rooms?
It depends how lucky we are. So the point is that this will randomly generate dungeons for us until we finally hit exits. Till we finally get to rooms that have 0 exits.
Right.
That make sense?
Yeah, but
So this might generate very, very complex ones,
that's what I'm saying.
or it might generate very easy ones. This is actually be really, this is going to be fascinating. Just for the sake of argument here, every single time we create a room, I'm going to print out creating a room. That way when we build our tree, since it's randomly expanding, we'll see how many times it happens to randomly call these things. Okay? You'll see what I mean here in a second. So this is what a room does. A room has treasure or it doesn't have treasure, and it creates rooms for its exits. Either 0, 1, or 2 exits. A cave only finishes on one of its branches when it finally has a room that has no exits. That make sense? Oh, this is going to be so easy to generate random caves. Awesome.
Yeah, but how we know like which
No,
room does not have the exit? So yeah, it will go on. So
Well, we'll see that. We'll see that. I'll give you enough to work on for that.
Create some cheat master key that shows like a diagram of all the rooms or no?
We could. I probably won't have you do that for homework. We don't have time to do it tonight. I'll probably do it next time.
Sure.
We certainly could do it. And it's not really complex, but it's not really what I want to get across for your homework assignment.
Right.
So it'd be interesting work, but busy work.
Okay.
Okay. So right now, this is all a room is. A cave has an entrance. So we create our constructor for our cave. Public cave takes no parameters. Entrance is equal to new room. I misspelled entrance up here. There we go. That's why I should always use this dot. See, I'm showing you why to use this dot so you don't misspell stuff. That's all cave is going to be right now. So this is all cave is. This is all room is.
So we're creating a lot of rooms, cave.
So it looks pretty simplistic, right?
Yep.
But when we run this, we're going to go out to driver. And in driver, all we're going to do is create a cave. And we should see a whole bunch of creating rooms.
Okay.
Yeah, and it's done. Look at all those rooms we created.
Can you go back to the
Like how we know how many rooms are created?
like? Can you go back to room?
Yeah,
Mine's
if
screwing
we
at
take
me for
unlimited or just
typo.
take a random number.
Hold on, one time. What do you want to see?
Room. Mine has a typo somewhere. It's got the little red thing.
Okay, so I'll leave that up. Your question. How do we know how many rooms it created?
Yeah.
Well, we could count this. Could count the number of rooms that are created. Right now, I'm printing it out. The reality is we don't necessarily care how many rooms are created. Actually,
Yeah, but we want like 2 rooms to exist.
actually we do care. Why do we care? Because
You need to know which room you are going to enter.
here, this will be, we're going to create another class here.
Okay, got it. Thank you.
Called stats. And stats is going to have a static, or here we're going to say private static int numRooms. Then we're going to have a public static void reset that sets numRooms equal to 0. And we'll have public static void add room, which says numRooms plus plus. Then we'll have public static int count, which returns numRooms. Return. Okay? So this guy's filled up with a bunch of class fields and methods. Only exists once. So when this guy's first created, he has a class variable called numRooms that is currently at 0. We can reset that because we might want that for different caves. But every time we add a room, we can do numRooms plus plus. I think this should work. So what I'm going to do here,
Yeah, but still we're adding the rooms are here, but we don't know like how many rooms.
well, we'll see. We'll see. So inside of room, every single time we create a room, here we'll leave the creating room in here. We'll also say stats.add room. So we're going to call this every single time we add a room. Then, out here in driver, we'll do a system.out.println number of rooms stats.count. So this particular cave had 171 rooms.
Okay.
That's a super, super, super interesting use of class variables. We needed to keep track of how many rooms we had, right? Well, we could do this a couple of different ways. One way is we could have created an instance variable. So maybe inside of cave.
I did it and I ran it a couple times. And the first 3 times I got 0. The second times I got 2 rooms. And this time I got 16,432 rooms.
See, it's all in the luck.
If you run again, so it will get the different values.
Oh yeah, we should get different values each time. There's 10 rooms, 620 rooms, 0 rooms, 19. That was a caved-in cave. That happens when you're spelunking.
Yeah, so it's getting random numbers every time.
Oh yeah, because our rooms are spawning new rooms. Spawning. That makes it sound like 40 times more complex.
That's because you're talking like in video game talk.
That's so good. But back to what I was saying here, this is a very interesting use of a class filled up with class methods and fields. I needed to keep track of some global information, right? So rather than passing around instances of something to every single room, so rather than a room taking no parameters, I could have passed it an instance of something and said, every single time you create another room, update this guy, which wouldn't have been wrong. In fact, you might even argue that's more right, because a lot of programming books say don't use global variables. But in this case, we just needed a convenient way of knowing how big our maps are, correct? Similarly, we could add to stats private static int num treasure is 0. You can zero it back out there. We can increment num treasure. Let's see. Let's call this guy room count and treasure count. Okay? So now we can keep track of 2 different statistics. So inside of our room, after we determine if there is treasure, we're going to say if this dot has treasure, if that's a true statement, stats dot add treasure. So now we'll also keep track of every single time we have a treasure. And only some of our rooms will have treasure in it, right? So back out here in driver, number of rooms will be stats dot room count. Number of treasure will be stats dot treasure count, which should be which will very, very, very likely be a smaller number than room count. Otherwise, every room would have had treasure.
Can you go back to it?
Yeah, 50-50.
Or 50-50-ish. So certainly you shouldn't have 600 rooms, 600 treasures unless you hit the lottery.
Yeah, for 600 room, we'll get 5 or 99. So, yeah, for main entrance, we don't have.
That's true, our main entrance. Well, main entrance could have treasure. Uh-huh.
Something wrong.
Yeah, something's wrong there. Number of rooms, 2, but the number of treasures is... Oh, wait. That is possible. That means every room did have treasure at that time. The top level one had treasure because we're only... our very first time we call room, we're not adding a room. We're not creating a room in our very first room. So for cave, we first create our new room. That room is not getting counted. But he might have treasure.
A new room?
Well, the only time we're adding rooms is right here, inside of this loop. So our very first room, if he happened to not have any rooms, this would be, our number of rooms would be 0 even though we had 1 room. Because the entrance is not considered a real room.
So should we just add +1 for, rooms?
We can do that. We can say inside of stats, num room starts off at 1.
That's what I meant to say.
Because we're assuming that the entrance is always there. But it may not have treasure. So here, number of rooms 730. Almost half of them. More than half of them has treasure. Okay. Does that make sense so far? All right. So not a whole lot of code at this point, right? So inside of our driver, well, we probably want to navigate our cave, correct? Which means that we need to have a way of displaying a room. So we're going to teach rooms how to display themselves. Displaying a room is going to say a room, whether or not it has treasure, and what the obvious exits are. Okay?
What about your message of a dark and murky?
Then every room will be dark and murky. For right now, we'll do.
Have sunlight shining into your cave?
We could randomly generate what the room looks like, but for right now, let's try to keep it relatively simple for the. Yeah. Sometimes there'll be a skeleton, right? So every room will say system.out.println a room. Here we'll put a little asterisks before and after for effect. Okay? Then, some rooms. So we'll say system.out.print treasure. If this dot has treasure, if that's true, system.out.println a pot of gold. Else, system.out.println none. Make sense? Okay, so every room might have a treasure. Some of them, there'll be a pot of gold. Other ones, it'll say none. Finally, system.out.print obvious exits. If the number of rooms is 0, that means there are no exits. We'll print out none. Else, there's at least one exit. Correct? So a room will display like this. So every room will have a little title up here that says a room. Then we'll have a prompt that says treasure, and it'll either say a pot of gold or it'll say none. Then we'll say obvious exits. If there are no exits, we'll say none. Otherwise, we'll print out 0 space 1, 0, 0 space 1 space 2, something like that. That make sense? That's what the output of a room will be.
Get rid of the creating a room line.
Yes. Okay. And I'll just start us off with a play method here. And this guy will say this dot entrance dot display. It'll display just the very first room. Here, I'll leave those couple of lines in there for us. So this is going to create a brand new cave. We won't have as much output now since we took that creating a room line out. But we'll see the number of rooms, the number of treasures in the entire cave, and then we should see it display the very first room. All the other rooms are there. You just don't have a way of getting to them yet. So that's your homework. We have 6 rooms. 3 of them have treasure. Here's our very first room. There is treasure in the first room. It's a pot of gold, and the obvious exits are 0 and 1. So from here, we should be able to say where we'd like to go.
And then you'll have a winner thing if you, when you get to the end of a cave, if your high score equals number of treasure, then you're a winner. Or, no, wait, that's just the total treasure. And
What are you
just
making?
kidding. I'm going ahead. Just okay.
Oh, for the treasure stuff?
No, I was thinking in a different path.
No, what I want for the homework assignment, I want us to traverse the tree. Yeah, remember I said it's going to be like a 2-class thing? Yeah, so I think that'll work out the best for this one. So we'll make it random guessing.
I was just wondering how it would calculate, like, what's the max number of treasure in a row.
Oh, that I thought about that too when we were doing it, because right now we're keeping track of total treasure. It might be difficult. Well, the answer to your question is something called a...
Well, can we just put a for loop inside a for loop and then go for that?
No, the real answer to your question is something called a depth first search. We'll talk about depth first versus breadth first searches next time. We'll actually have to write something that will literally traverse our tree in every possible way.
Yeah.
To figure out what the best thing is. It'll be way more complicated than a for loop inside of a for loop. Because we're literally going to have to, at each room, try all the possibilities. Yeah. It'll be very it's going to be an interesting problem, but not something we can finish today and not something that we can reasonably do for homework. But we will solve it next time. Because that will be part of what's the best, because that's the point of solving our puzzle. When did you get your best? Okay? But for the first part of the assignment, we're going to start from here. And what you need to be able to do is just traverse your cave until you hit a dead end. You don't get to return to the beginning. You basically keep going as long as you have exits. So I'll fill in one more little line here. I'll say system.out.println. What would you like to do? You might want to add crap here. Okay? So that's probably where we'll do some user input and that kind of stuff. So if I run this right now, it's going to show us that we have 2 rooms. One of them has treasure. It's in the very first room. We're not even calculating treasure at this point. Okay? We're just traversing. We have an obvious exit to direction 0. What would you like to do? We should be able to, at this point, hit a 0, and it should take us into that room. Okay? Show us the next room.
Mm-hmm.
All right? So we need to traverse this cave. So now as you test this, sometimes you'll get lucky and you might be able to get 5 or 6 or 7 doors down. 50, something like that.
Could we put a limit on how many, like...
There's no limit.
Yeah, I would say no limit at this point. Because right now, I mean, sometimes we run this, we get thousands of rooms, right?
Mm-hmm.
So, but for testing it, you don't have to have it start over. So here, let me just write the words down. That way you can ask any questions. So I'll put your assignment up here. And then we'll put the paper up here as well. Okay, this is actually Unit 2. And let me... Everything's saved in here. Yep. Let me just zip that up real quick so I don't forget to attach it. What's your email address again?
Me?
Yep.
Lauren at avconsulting.net.
Oh, Lauren at... See, now I won't forget. Okay. Update the crawler game attached to allow a user to traverse the cave. They should be prompted in each room to pick an exit for right now, let's say, or quit. The quit will be what we replace to start over next time. Okay? Every room they enter that has a treasure, they should earn 1 point. Once they quit, the total number of treasure collected should be displayed to the screen. You should also display the total number of rooms visited. Your hint there is you will solve that problem very similarly to how we solved the statistics problem. My stats class is exactly what you want to do for those two things. Should not be difficult. Okay? You do not need to let them start over, and you cannot move backwards in the cave. Make sense? Enter the cave, traverse it till you hit a dead end or choose to quit, spit out number of rooms you visited, number of treasures you collected. Make sense? So basically what you're doing for this assignment is you are traversing a tree data structure that we happen to have called a cave, whose nodes happen to be called rooms. Okay, questions about what I'm asking you to do for that? Let me attach the code, then we'll talk about the paper. Okay, so that's the homework assignment. Then, report number 3. Write a 2 to 3 page paper discussing the concept of a MUD as it relates to multi-user dungeons. So very related to what you're building. These were text-based Dungeons and Dragons games, similar to what you are writing in your homework assignment this week. What was the first MUD? What were the different types of MUDs? Do people still play MUDs today? And then what modern game genre has replaced MUDs? Let's call it largely replaced MUDs. Make sense? All right, questions about that? Comments, concerns? All right, I will see everybody next Monday. Don't forget to submit your self-evaluation for each thing too. Well, for your homework assignment that I just assigned to you now. If you didn't do it for your homework assignment due today, go in and submit it right now. Because I'll probably grade those in the morning.
Yeah, we did.
Okay. Stop the recording.